Hello students, welcome to lecture 26 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on superlens, hyperbolic metamaterials and hyperlens. So here is the lecture outline. We will see the idea of perfect lens, and to achieve that how far we have gone till now. We will see a version of superlens. We will then discuss the optics of anisotropic media that will allow us to understand how hyperbolic media works, and this hyperbolic metamaterials will allow us to obtain hyperlens, and then we will also see the applications of hyperlens. So, for centuries optical lenses have been one of the prime tools of the scientists. It allows us to look at objects which are very tiny. So, you can focus light and that allows you to image a particular tiny object. That is how lens works. Now, their operation is well understood on the basis of classical optics. So, there is a curved surface and that helps us focus light by virtue of the refractive index contrast. Equally, their limitations are also dictated by wave optics. So, no lens can focus light onto an area which is smaller than a square wavelength. So, typically if there are two objects which are separated by a gap which is less than lambda by 2, you will not be able to see them differently. Now, this is the problem with the conventional lenses. So, what is then new to say that other than polishing the lens more perfectly or to invent slightly better dielectric which can have a better focusing ability, can we improve that resolution and go and see objects perfectly, and that would be a perfect lens. And that quest was solved when Professor Pendry proposed the idea of negative index materials. So, if there is a material with negative refractive index n equals -1, you can use this as an alternative to your conventional lens. So, this kind of material they can have parallel sides, okay, but then they are still able to focus light at a particular point, as you can see here. So, here is the point source, here is a slab of negative refractive index material, okay, and the light gets again over here, and then when it exits it again focuses at this particular point. So, you are able to get a point source focused here with the help of a negative index material. Now, if you look into the picture carefully, you can see that the Snell's law of refraction at the surfaces are actually followed, just that at negative refractive index material they actually make a negative angle with respect to the surface normal. So, instead of bending this side, they are actually bending on the opposite side, okay. So, they are bending towards negative theta angle, okay. And another important characteristics of the system is basically the double focusing effect, as you can see here. So, it is actually doing double focusing, okay, and the underlying secret of this medium lies in the fact that both dielectric function permittivity and magnetic permeability both happens to be negative, okay, and you get n equals -1, okay. So, how it works? So, n is typically taken as square root of epsilon mu, when epsilon mu both are -1, okay. So, you get, okay, to judge this particular square root, you have to take the negative sign for that, okay. So, that allows you to get n equals -1. But if you look into the impedance of the medium, impedance can be calculated as this formula, z equals square root of mu epsilon naught over epsilon mu naught over epsilon naught. Now, here if mu and epsilon are both negative, they do cancel out each other, okay, and in that case you will get that the impedance is basically same as that of the free space. So, it is matching perfectly with the free space, and that is why this kind of a interface will never show any reflection. Moreover, at the far boundary here again there is an impedance match, and that is why light can perfectly transmit into the vacuum. So, this is how you can actually realize a perfect lens. But then, as you know that for every wavelength to get material permittivity and permeability both to be negative and -1 is very difficult. Okay. So, people have tried some easier version of achieving this kind of a functionality, and those kind of lenses are called super lens. Okay. So, they have focusing capability better than the conventional lens, and that is why they are called super lens. So, what actually decides the resolution of a conventional optical lens? That is, with the lens which has got permittivity positive and permeability positive. So, they are typically constrained by the diffraction limit. Okay. And this happens because of the fact that the evanescent wave which contains the sub-wavelength information, that decays exponentially with distance, and it is basically undetectable for the conventional lenses to image. So, you are not able to capture any information which is coming from a sub-wavelength source or sub-wavelength object. So far the information carried by these evanescent waves can only be gathered by NSOM, that is near field optical microscopy techniques. Okay. Now, in negative refractive index media, there is something magical that happens with this evanescent wave. Evanescent waves in negative index material can actually get magnified, okay, and that happens exponentially with distance, and that helps you to get the sub-wavelength details retained for imaging by a conventional lens, and that allows you to break the diffraction limit of light for conventional imaging. However, there is a small problem that inside the negative index material evanescent wave does get amplified, but outside of that material it again decays. Okay. So, you cannot image this particular information from far field, you still have to do the detection at the near field. Okay. So, super lens does one good thing, it could amplify and extend the evanescent field, but it cannot change the decaying characteristics. So, if you put the conventional media, the normal lens that you see every day, they do not do any good to the evanescent waves. Super lens, they magnify the evanescent waves, but outside that again decays. But then you are actually looking for something that is capable of converting these evanescent waves in some form of propagating waves. Okay. So, that is what you are looking for. If you are able to do this, then you will be able to image this object using a far field technique. Okay. And this is where the hyper lens will come into picture, right. So, as I mentioned, an ideal device would convert the evanescent waves to propagating waves for ease of detection and processing in the far field. So, mathematically let us look into the situation, how it looks like if you take evanescent wave in ordinary material, you can write the electric field as Ez, that is given as E naught exponential j k prime plus j k double prime n z. So, if you open this up, you will see that there are two components. One has got e to the power j k prime n z, and that is basically the oscillating component of the wave, and then you have e to the power minus k double prime n z, that is actually the decaying component or the evanescent component. Now, if you write the same wave equation in a negative index material, you can replace this n by a minus n, and then you will see that instead of this guy getting a minus k prime, you are actually getting a positive factor here. So, this oscillating part remains same, okay, but this decaying evanescent component is now a growing evanescent component. So, that is the main difference between the evanescent waves when propagating in a negative index material. In short, evanescent field grows in amplitude inside negative index materials. So, if you use a negative index material slab as lens, you can see that you are actually able to obtain a super lens where light can be focused at a particular point perfectly, okay. And this particular plot shows the evanescent field, okay, which is getting amplitude. What is this one? This is showing the propagation, like the propagating wave, that is perfectly fine. So, these are basically propagating waves. So, they are happily propagating inside this material without any change in its intensity or amplitude. However, if you see the evanescent field, they get amplified when they are traveling inside the negative index material, but as soon as they leave, they again decay, but then that gives you that extra distance, you know, to image them using near field techniques. Now, let us look into a poor man's super lens. Okay, the name itself tells you that, you know, it is not a perfectly made lens, super perfect lens, but it is a close approximation, or you can say a rough approximation of similar kind of feature. Okay. So, nevertheless, applications that involve distances smaller than a wavelength, such as near field microscopy, this kind of techniques may significantly benefit from a simplified version of the super lens. So, here is an object that you are trying to image, and you can actually think of a poor man's super lens made of a material which has got just negative dielectric permittivity. Okay. So, you are not looking for both epsilon and mu to be negative, you are just looking for, you know, negative permittivity material, and the easy choice could be a silver super lens. So, that is why it is called a poor man's super lens. Reason is that this negative dielectric permittivity alone is much easier to realize, because there are naturally occurring materials like metals, gold, silver, they all have negative permittivity at optical frequencies. So, if you put this kind of a thin slab material next to your object, what happens? Okay. So, the evanescent field will get amplified in it, and that will help you to do the imaging. Okay. So, the purpose here is a thin slab of metal should have a permittivity equal and opposite to that of the surrounding media. The reason is you need to get rid of the reflection by doing impedance matching. So, that can give you a poor man's super lens in the quasi-static limit. Okay. And what is the benefit of this kind of a super lens? They can form an image with sub-wavelength resolution in the near field. So, remember here they are still doing the imaging in the near field, just that this kind of a lens allow you to do sub-wavelength imaging with ease. Okay. Now, let us look into some super lens examples. So, one example is this particular experiment where an arbitrary object nano was imaged by a silver super lens. So, this particular object was inscribed on a 50 nanometer thick chrome, and then there was a 365 nanometer light which was used for illumination. Okay. And there was a photoresist layer on the other side of the silver super lens to capture the image of this particular object. Okay. And these are the different types of images that has been taken. So, this is the focused ion beam, or you can say FIB image of the object. So, here you can see that the line width of the NaNO object is basically 40 nanometer. The second one shows the atomic force microscopy, or AFM image, okay, that is developed with the photoresist and with the in the presence of silver super lens, and this is the same experiment without this silver super lens. Here the silver is basically replaced by this PMMA spacer. So, here you can see that the resolution has gone bad, and the line width has substantially increased. Okay. So here you can see the cross section, the average cross section of the letter A shows an exposed line width of 89 nanometer. This is the case when you are having the silver super lens, but when you don't have it, without the silver super lens, the maximum width, or you can say half maximum line width, significantly increases and it goes to 321 nanometer. So you actually lose the resolution. Okay, in that case you will not be able to see those, if there are tiny objects which are very closely spaced, you will not be able to image if you don't use the super lens. Okay, so people have also used negative index metamaterial lens for sub-wavelength microwave detection. So this is a very common structure that you see in microwave for realizing negative index metamaterial. So here it is a periodic arrangement of split ring resonators and wires. So we have seen this kind of arrangement. There are vertical wires and on top of that you have this ring kind of thing, which are basically split ring resonators, and you can print PCBs based on this and put them in a layer, and this particular structure exhibit effective negative refractive index over a range of frequencies upon certain specific incident wave polarization. Now what is the benefit of this? When you put this metamaterial lens and you have a transmitter monopole, and this is the scan region. So when you do the scanning, you could see that you are able to obtain a focal spot at a distance of 30 nanometer from the lens, and if you take the width of this focal spot, you can get that it's around 30 nanometer. So this is the full width half maxima, because this is taken at the minus 3 dB point, or where the amplitude is half. So that is the case that using this metamaterial lens you are able to focus, or you are able to focus at this particular point. So there are experiments conducted at 1550 nanometer as well for imaging of sub-wavelength resolution by metamaterial nanolens. So in that case you can think of nanolens, which consist of high aspect ratio metallic wires which are embedded in a host dielectric medium, and then this is the object. Okay, so and people have collected the SEM image of this NEU letter. So NEU stands for Northeastern University, who conducted this experiment that was basically milled in a 100 nanometer thick gold metallic film, as you see at the back. Okay, and the letters have 600 nanometer wide arms. So this is the width of this arm that you can see. Okay, and this is the lens, and this lens actually allow you to capture the evanescent waves and amplify them so that you can clearly capture the image of this particular object. So that is these are a couple of examples of super lens, okay, that people have used in different frequency regime. Okay, now the whole idea here is to go for imaging at far field, and that is where hyper lens, which are made from hyperbolic metamaterials, would be very interesting. So in those cases what happens, you will be able to convert the evanescent wave into a propagating wave, and that is why you can do the imaging from far field. So once again, if you look into this diagram, the blue wave shows the normal propagating wave. So in all three medium, the normal propagating wave simply propagates without any change in amplitude. You can see that they are just propagating. Okay, but evanescent waves simply decays in a conventional media. Inside a super lens or negative index material, you can see that evanescent waves get amplified, but as soon as it leaves that material, it decays again. It remains like decaying evanescent wave, but in hyper lens, evanescent wave enters and leaves as a propagating wave, and that is something very cool, because you can actually use this kind of material to extract sub-wavelength information and image it from far field. Okay, so hyperbolic metamaterials are basically anisotropic media. So, when we say anisotropic media, we are basically telling that the macroscopic optical properties of that media depend on directions. So, let us quickly look into some of the optics of anisotropic media. The first parameter that comes to mind is permittivity tensor. So, if you remember that this epsilon is the permittivity, but in the case of a linear anisotropic dielectric medium, the displacement field dI looks like summation of j epsilon ij times Ej. Okay. So, epsilon ij is basically the permittivity tensor. What are these indices I and j? They are basically 1, 2, 3, they refer to the x, y and z components. So, here you can see the dielectric property of the medium are basically characterized by a 3 by 3 array of 9 coefficients, and that forms a electric permittivity tensor epsilon. And the material equation remains same, that is D equals epsilon E, but here epsilon is basically a tensor. Now, for most of the dielectric media, it has been found that electric permittivity tensor is basically symmetric. So, epsilon ij is same as epsilon ji. So, in that case, the relationship between D and E are also reciprocal. That means their ratios remain same if their directions are changed. So, in that case, the elements of the permittivity tensor depend on how the coordinate system is chosen relative to a crystal structure. However, it can be done very smartly, because you can always find a coordinate system where the off diagonal elements of this epsilon ij will vanish, so that you will be able to write d1 equals epsilon 1 e1, d2 equals epsilon 2 e2 and d3 equals epsilon 3 e3, where epsilon 1 is basically the epsilon 1 coefficient, epsilon 2 is basically epsilon 2 and epsilon 3 is basically epsilon 3 coefficient. So, these are basically the diagonal coefficients, and all of diagonal elements are basically 0. Now, E and D are parallel along these particular directions, so that if, for example, E points in x direction, D has to also point in x direction. Now, this coordinate system defines the principal axis and the principal planes of the crystal. So, the permittivities epsilon 1, epsilon 2 and epsilon 3 will correspond to the refractive indices n1, n2 and n3. You can write n1 equals square root of epsilon 1 over epsilon 0 and so on. What is epsilon 0? That is the permittivity of free space, and this n1, n2 and n3 are known as the principal refractive indices. So, that brings us to the different classification of crystals. So, you can have biaxial crystals where the 3 principal refractive indices are basically different. You can have uniaxial crystal. So, these are the crystals with certain symmetries where 2 of the refractive indices are equal, say n1 equals n2, and the third one is different. So, in case the indices are denoted like this, n1 is written as n is equal to n2, can be written as NO, that is the ordinary indices, and n3 is basically NE, that is the extraordinary index. Okay. So, that will be index. Okay. So, you can call the crystal to be a positive uniaxial crystal when the extraordinary refractive index is larger than the ordinary refractive index, and you can call it negative if it is other way around, that is NE is lesser than NO. And the z axis of the uniaxial crystal is called the optic axis. So, in certain crystals with even greater symmetry, okay, such as those with cubic unit cells, okay, all 3 indices will be equal, n1 equals n2 equals n3, and those are typically the optically isotropic crystals. Now, the next important topic is impermeability tensor. Now, when we read about this relation T equals epsilon E, you can always think of an invert relationship, that is basically E equals epsilon inverse D, where epsilon inverse is basically the inverse of the tensor epsilon, and it is useful to define this tensor as a electric impermeability tensor eta. So, eta is defined as epsilon naught epsilon inverse, and do not confuse this eta with the impedance of the medium eta. Okay, these two are different concepts. So, here you can write epsilon naught E equals eta d. So, epsilon is symmetric, that makes eta also symmetric. So, both epsilon and eta, they share the same principal axis. Now, in this case the principal coordinate system, in the principal coordinate system eta is diagonal with the principal values given as epsilon naught over epsilon 1 equals 1 by n1 square, epsilon 2 by epsilon 0 by epsilon 2 will be given as 1 by n2 square, and epsilon 0 by epsilon 3 will be given as 1 by n3 square. Okay. So, either this tensor permittivity or impermeability, okay, they can fully describe the optical properties of the crystal. So, you can either use any one of them. The next important parameter or the concept is called index ellipsoid. So, index ellipsoid is also called as optical indicatrix. So, this is an quadratic representation of the electric impermeability tensor, which is eta, okay, and as you have seen, it is written as epsilon naught epsilon inverse. So, you can write this equation, the summation over ij eta ij xi xj should be equal to 1. What is ij? They are 1 to 3, they show the different directions. So, if the principal axis were to be used as the coordinate system, you come up with this equation, that is x1 square by n1 square plus x2 square by n2 square plus x3 square by n3 square equals 1, and that is the equation of a ellipsoid, and we call this an index ellipsoid. Okay, and this is how it will look like. So, n1 n2 and n3 are these points, okay, and x1 x2 and x3 are the coordinates, or you can say the principal axis. Okay. So, the optical properties of the crystal are completely described by its index ellipsoid. For a uniaxial crystal, okay, the index ellipsoid reduces to an ellipsoid of revolution. So, it looks like a ellipsoid like this. So, it can be a prolate or oblate shape depending on whether it is a positive uniaxial or negative uniaxial system. Okay. Prolate means like a kind of rice grain, okay, and oblate looks like a gems. Okay. And for isotropic medium where n1, n2 and n3 are equal, you can understand this ellipsoid will reduce to a sphere. So, in all direction, you know, the property is the same, and that is what isotropic means. So, index ellipsoid for a isotropic material is a sphere. The next important concept is the dispersion relation, the K surface. So, consider xyz be a coordinate system that coincides with the principal axis of a crystal. Now, you are considering light propagating through it. What will be the normal modes? Now, the normal modes of a light propagation through this kind of a crystal are basically those states of polarization that are not changed when the wave is transmitted through the system. So, if you consider normal modes for propagation in z direction, that will be linearly polarized waves along x and y. So, there are two normal modes. So, in this case, so to determine the normal modes for a plane wave that is traveling in the direction of u cap, it can be any arbitrary direction. The material equation D equals epsilon E, okay, that allows you to write down the Maxwell's equation like this. Okay. So, we know this from the Maxwell's equation, and when you put this value into this equation, the value of H, okay, you can have everything in terms of E, and then D you can replace with epsilon E, okay, and you finally come to this particular equation. Okay. So, this vector equation, okay, which the electric field has to satisfy, it basically translates to three linear homogeneous equations for the components E1, E2 and E3. Okay. So, these are basically the components along the three principal axes. Okay. And you can write down the vector equation in terms of a matrix or in the form of a matrix, and it looks like this. So, here k1, k2, k3 are basically the components of the wave vector k. K0 is the vacuum wave number, which is omega over c naught, and n1, n2, n3 are the three principal refractive indices. Okay. So, when the determinant of this matrix goes to 0, a non-trivial solution for these equations yield the dispersion relation. So, this is a compact form of the equation. It reads summation over j equals 1 to 3 kj square over k square minus nj square k naught square equals 1. So, that is the equation of the dispersion relation or the k surface. So, in the case of uniaxial crystals, you have N1 equals N2, which are basically the ordinary one, NO, and N3 is NE, and in that case the equation of the k surface, so the equation looks like omega equals omega. Now, this is basically function of k, so k1, k2, k3, and you can write this equation in this form. So, here you will see that this particular equation has got two solutions, one of the sphere that corresponds to the leftmost factor vanishing. So, you can write k equals n naught k naught, and other one is this one that corresponds to a ellipsoid of revolution, okay, that vanishes this factor, and you can write that equation as this plus this equals k naught square. So, this is how you can put it on the k surface. So, here is basically the plot of the k surfaces, okay, with the yz plane. So, you are only showing k2 and k3 here, okay, and we are considering a positive uniaxial crystal, and that is why you are able to see Ne larger than No. Okay. So, here you see the sphere that corresponds to this one, and this is the ellipsoid, which is this one. Okay. Now, when you say k surface, what are k surface? It is a centrosymmetric surface which comprises two sheets. So, each corresponding to one solution, that is a normal mode. Now, in the case of biaxial crystal, and if you consider N1 smaller than N2 smaller than N3, then these sheets they meet at 4 points defining two optic axes. So, a biaxial crystal will have two optic axes, okay, and you can see that if you consider one octant of the k surface, so there you will see that there are already you can see the one optic axis. In the other octant you will be able to see the other one. Okay. In the case of uniaxial crystal, where N1 equals N2 equals NO, that is the ordinary refractive index, N3 is the extraordinary one, the two sheets become a sphere and a ellipsoid of revolution, and they meet at only 2 points. That means that we will have only one single optic axis, and that is also along Z. So, you can actually see they are meeting here and also at the bottom. So, this is the top, you will also have same thing happening at the bottom. So, you can actually see that this is along the Z axis, and in the case of isotropic, where N1, N2, N3 all are equal to N, the two sheets degenerate into a single sphere. So, they overlap and you will just get this one, right. So, this builds up the foundation to introduce hyperbolic media here. Now, let us look into the concept of isotropic media, which has got permittivity and permeability tensors with positive and negative principal values. Till now we have considered all the positive values. Now, the designation of the medium as double positive, single negative, double negative will all then be dependent on the direction of propagation of the wave as well as on its propagation polarization. So, to demonstrate one kind of this rich behavior, so let us consider a media with isotropic magnetic properties, and let us consider positive permeability, but we have anisotropic dielectric properties. So, one more time we are considering mu to be isotropic and positive. So, we are not we are just keeping it fixed, okay, and same throughout, but then epsilon is anisotropic. And in such a media, wave propagation will be described by its the positive values of the electric permittivity tensor, okay, epsilon, that is epsilon 1, epsilon 2 and epsilon 3, okay. And in the case these parameters, when they take up mixed signs, the wave propagation will start showing some unusual properties which you have not seen in the previous cases. So, to understand this better, let us first consider the special case of a uniaxial crystal with epsilon 1 and epsilon 2 to be positive, and compare the wave propagation when the media has got a positive epsilon 3 and a negative epsilon 3. So, let us first consider the positive epsilon 3 case, okay. And here we have seen that the dispersion surfaces, which are also called the K surfaces, or you can say omega k, for the ordinary wave are basically like a sphere, okay. So, you have got k equals n naught k naught, where n naught is basically square root of epsilon 1 over epsilon 0. But the extraordinary wave, it saw a quadric surface, and that is basically the ellipsoid. So, you can write this as this particular ellipsoid equation. Now, in the uniaxial crystals, the index ellipsoid is basically an ellipsoid of revolution. So, this is how you can represent that, okay. Now, if you consider a wave that is traveling along a direction, arbitrary direction of u cap, okay, and it forms an angle theta with the optic axis, okay. So, what will happen in that case? So, it will have a index ellipse, okay, with half lengths n naught and n theta. Now, what is this new concept called index ellipse? So, it is basically when you have this direction given to you, that is the direction in which the wave is propagating, you can draw a plane through the origin of the index ellipsoid that is normal to u cap, and the intersection of this plane with the ellipsoid will give you this index ellipse, okay. And the half lengths of the major and the minor axis of the index ellipse are basically the refractive indices NA and NB of the two normal modes. Now, here we have seen that this is NO and this will be N theta, okay. So, N theta needs to be determined from the index ellipsoid equation. So, there you can actually make so this is the index ellipsoid equation. So, there if you make certain substitution like x1 equals n theta cos theta, okay, x2 is 0, okay, and then x3 equals minus n theta sin theta, you can get this is the equation that relates your n theta with NO and NE, okay. So, you can actually obtain that the normal modes will have refractive indices. So, NB is basically NO and NA is basically your N theta. So, why this is required? This is basically a generic case. If the wave propagation was along the axis, optic axis, then it is very simple, but if it is not, then this is how you should be able to find, okay. You have to find out the normal modes and what are the refractive indices of the normal mode. So, you have to take help of the index ellipse. So, normal modes have refractive indices NB equals NO and NA equals N theta, and the first mode, which is the ordinary wave, as you can see that it has got a refractive index that is independent of theta. But in accordance with the ellipse, the second mode, which is called the extraordinary wave, okay, it has got a refractive index n theta, and that varies from NO to NE when your value of theta is changing from 0 to 90 degree. So, that can be seen here. So this is another representation. So if you have the axis, this is the k vector that is making a theta angle with it, and this one is your basically NO, and this is NE, and this is the angle theta. So when theta is 0 degree, your n theta is basically NO, and when theta is 90, your n theta is basically NE. So you can actually land up anywhere depending on the direction at which the wave is propagation through the crystal. So we understood that when epsilon 3 is positive, the extraordinary k surface is basically an ellipsoid, or you can say it's an ellipsoid of revolution. Okay, it's a 3D thing. Now in this particular figure, what is shown is the contour of the k surface in k2 k3 plane, and we have considered a uniaxial anisotropic medium where we consider epsilon 1 and epsilon 2 to be equal and positive, and epsilon 3 is also taken to be positive. Okay, so we have marked the theta angle here for reference. So this contour is shown only for the extraordinary wave. You already know that for ordinary wave is basically a sphere. So here the k contour is a ellipse, and this medium is DPS double positive for all the direction of propagation, because in all cases mu we have already taken as positive and isotropic, and in all cases epsilon 1, epsilon 2 and epsilon 3 they are all positive. So this is a DPS medium, right. So this we have already seen is that NO is basically the ordinary index, and NE that is given as square root of epsilon 3 over epsilon naught. Okay, that can vary from so n theta can actually vary between NO and NE when the angle of theta is changing from 0 to 90 degree, and epsilon 3 is positive here, so NE is always positive. So that makes it a DPS medium. Now consider the case when epsilon 3 is negative. So in that case, the extraordinary k surface, which was previously a ellipsoid, that will take the form of a hyperbola, okay, or you can say it's a hyperboloid of revolution. Okay, and this such medium is known as hyperbolic medium. So in this case, the refractive index n theta for the extraordinary wave at an angle theta in the k2 k3 plane will be given as this 1 over. So you can do the same process that we have seen before, and you will get this particular expression. Here NE is basically square root of mod epsilon 3 over epsilon naught. Why mod? Because epsilon 3 here is negative. So if you do that, you also know the theta can increase from 0 to theta max. So what is theta max? Theta max is given as tan inverse of NE over NO. Okay, and that can make your refractive index n theta starting from n0 to infinity. It means you can go to a very large refractive index using this kind of a medium. So this signifies that the wavelength inside this medium can be very small, okay, because n is almost infinity, very large, and when n is very large, you can also slow down the wave to almost a halt. It's like extremely slow speed of wave propagation when your theta is approaching theta max. So this is the same contour of the k surface that you have seen before, just for the case of here it is epsilon 3 is negative. So the contour of the k surface in k2 k3 plane for uniaxial anisotropic medium where epsilon 3 is negative, epsilon 1 and epsilon 2 are same and positive. So the k contour is basically hyperbola, and the wave can propagate in the direction that lie between the cone, this particular cone, okay, of the half angle theta max. So what is theta max? So this is theta max that you can see here. Okay, so if you actually go beyond theta max, okay, the medium will act like a single negative medium, and it will not support propagating waves. So you have to be within this half angle theta max. Okay, so you be within this cone. Now, how do you make hyperlens based on this hyperbolic metamaterial? Now, an important property that you have seen of hyperbolic medium is that the plane wave with wave vector components k1, k2 and k3, it does not matter how large your k1 and k2 are, okay, there is always a real value for k3 that will satisfy this equation. Now, that tells you that when epsilon 3 is negative, okay, the wave can actually propagate through that medium, okay, and this signifies that the spatial frequencies greater than an inverse wavelength in any plane do not correspond to evanescent wave in such medium, okay. In ordinary medium they do, but here it is not. Here they are basically, they can be transmitted over long distances, and this is the beauty of this hyperbolic metamaterial. So, although propagation is accompanied by Fresnel diffraction, the hyperbolic medium has a transfer function with no spatial frequency cutoff. So, it can actually take care of all spatial frequencies. So, moreover, Fresnel diffraction may be significantly reduced in a hyperbolic medium. We will not go into that details of Fresnel diffraction here, but we will just tell you the concept how this hyperbolic metamaterials can be used as a hyperlens. So, we have seen that NO is, in the case NO is much lesser than NE, okay. What you can have? You can have theta max, which is given as tan inverse. So, NE over NO, and NO is very small. In that case, theta max approaches 90 degree. So, this surface 90 degree means like this. So, this surface is almost becoming a plane, okay. So, the hyperboloid of a revolution flattens and therefore approximately becomes planar, and when it becomes planar, you can see that it will correspond to a constant k3, okay. So, when it becomes planar, so it will have a constant k3 for all the values of k1 and k2, right, and the transfer function e to the power minus j k3z, which is associated with the propagation in the slab, will then be independent of the spatial frequencies k1 and k2 of the input field distribution. And how it helps? A point in the input plane is thus imaged to a point in the output plane, and the propagation may be described by ray optics. This particular slab in this situation can act as perfect near field imaging system, okay, like this. So, you can actually have sub-wavelength resolution, but because of this hyperbolic medium, you can use ray optics information and get this tiny information converted into waves, okay. So, this is basically showing a hyperbolic slab with a planar dispersion relation. How do you get planar dispersion relation? When theta max approaches pi by 2, you will get like a plane, okay, and it is becoming k3 becomes constant for all values of k1 and k2. So, you are getting a planar dispersion relation. So, the propagation along your optic axis direction, that is the z direction, which is this one, will become diffraction free. So, this kind of slab can then be curved in a way that image can be geometrically magnified, as you can see in this particular figure, okay. So, here, okay, you are still having evanescent waves, okay, but then when you curve it like this, okay, you can actually have these three components magnified, and you are getting a much magnified version of image here, and this can actually give rise to this can be imaged as propagating waves from the far field. So, the concept here is, if the spatial frequency components of the magnitude image become smaller than the inverse wavelength, they generate propagating waves. Now, this is the funda behind this hyperlens, and once you generate propagating waves, they may be captured with the help of conventional lens. So, you do not need a NSOM, near field microscopy technique to do this, you can simply do the far field imaging. So, let us look into this diagram once again, because this is the heart and soul of hyperlens. So, here you have a hyperbolic slab which has got epsilon 3 negative. What is happening to epsilon 1 and epsilon 2? Both are positive, okay, and equal, but they are much smaller than the value of epsilon 3, which is the modulus of epsilon 3. This is required to get a planar dispersion function, okay, so that you get k3 equals constant, okay, and that will make your propagation along the optic axis, that is in z direction, diffraction free. So, you can simply propagate like this without deviating here and there. Now, when you make a hyperbolic slab curved into something like this, so it form a inhomogeneous cylindrical structure with the local optic axis pointing in the radial direction, okay. So, this acts as a magnifier of the sub-wavelength details. So, if you have some objects, a few objects which are in sub-wavelength scale, you can actually magnify them and bring it to a larger scale. And if the details of the magnified image are larger than the wavelength, they can produce propagating waves, and that can go to the outer medium. So, this is the concept. So, why you are using this curved thing? Curving allow you to separate them, understood, and getting this planar dispersion relation makes it diffraction free. So, you can specifically say that this point is now magnified onto this one without any kind of overlap, understood. So, that allows you to do the imaging, and this cylindrical slab is known as the hyperlens. So, here are some examples, if you can see. So, here are some sub-wavelength objects that were imaged using hyperlens. So, hyperbolic metamaterials in curved geometry, they result in hyperlenses, okay, and with corresponding dispersion represented in cylindrical coordinates. Here you can see we are using cylindrical coordinate system, rho, theta, z, okay. This is planar. So, you are simply having Cartesian coordinate system, but when you convert it into cylindrical shape, you bend it, you use this coordinate system. Similarly, you can write k rho and k theta. Here you are just talking about kz and kx, okay. Now, for the sub-wavelength object placed at the inner boundary, wave propagates along the radial direction. So, when they propagate along the radial direction, they gradually compresses its tangential wave vectors, and that is how they give you magnified images at the outer boundary, because the radially they go out, okay, and you can get a magnified image. And once that magnified image is larger than the diffraction limit, it can be easily resolved using far field. So, here is an example of such hyperlens in application. So, you see, if you simply have air and there are two objects which are just separated by 80 nanometer. So, these are sub diffraction limited line sources, and only here you are able to do the far field imaging, but you cannot resolve. You cannot say that there are two sources. You think that there are like only one source, okay. But when you have, first you have this kind of hyperlens put on top of your these two line sources. So, they diffraction freely they go, and then they create a bigger image, and when they are above the diffraction limit, they can be imaged using the conventional technique. So, they can propagate in air and give you the information that there are basically two sources, right. And these are simulation results. Here the radius of the hyperlens at the inner and the outer boundaries are taken to be 240 nanometer and 1200 nanometer. The permittivity of the metal and dielectric that is used for making this hyperbolic metamaterial or hyperlens is taken as this 2.3 minus 0.3 I, and the dielectric one is simply 2.7, and the filling ratio is taken to be 50%, and this is how it shows that you are actually able to do very good imaging using hyperlens. So, with that we will stop here and we will start the discussion of tunable photonic metamaterial based devices in the next lecture. In case you have any doubt regarding this lecture, you can always drop me an email mentioning MOOC in the subject line. Thank you.